first event for Solar Energy Speaker Series. My name is Valentina, class of 27. There's Eleanor McGath, class of 28, Emily Lester, class of 28, and Ethan Rodriguez, class of 27. And we are an initiative of Green Team called the Net Zero Project. Our goal is to promote education, awareness, and engagement around Dennison's commitment to net zero carbon emissions by 2045. By doing so, we hope we can maintain momentum towards this commitment. A landmark achievement towards this commitment is Denison's ongoing installation of a solar array that will meet 50% of Denison's electric and energy needs. To celebrate this milestone, we are hosting a series of speakers to talk to the Denison community about the many possibilities offered by solar energy. We will have 3 more of these solar energy talks throughout the semester, centering research as well as other career opportunities in solar. So stay tuned. But for now, let's introduce our speaker for today, Dr. Katz. Dr. Jordan E. Katz is an associate professor and chair of the Department of Chemistry and Biochemistry at Denison University. He specializes in materials and physical chemistry, focusing on the synthesis and characterization of semiconducting nanomaterials for solar energy applications. His research aims to develop low-cost, self-assembled nanostructures and employs electrochemical and spectroscopic methods to understand interfacial electron transfer reactions in solar cells. Dr. Katz earned his BA in chemistry from Reed College. He was a Fulbright scholar at the EPFL in Switzerland. He completed his PhD in chemistry at the California Institute of Technology under the guidance of Professor Nathan S. Lewis. Following his doctorate, he conducted postdoctoral research at the University of California, Berkeley, and Lawrence Berkeley National Laboratory. Since joining Denison University in 2010, Dr. Katz has been an active researcher and educator. His work has been published in various scientific journals, and he holds a U.S. patent for a high-throughput screening device for photocatalysts. Please join me in welcoming Dr. Katz.
Thank you, Valentina, for that introduction, and thank you to the Green Team for inviting me. It's really a pleasure to be here. Thank you all for coming. And maybe ironically, as the slide for my title, I chose a picture of the Earth in which it is night everywhere and the sun isn't shining. But this picture illustrates, I think, some important ideas about where energy is consumed in the world. And it's sort of a mixture of both where the people are, not so many people in the middle of Africa here or in the middle of Australia, but also where people have access to electricity. So there are many regions in Africa where there are very high population centers, and you can see that it is not lit up like places like the States and Europe, Japan here. So it's just sort of an interesting look at who has access to energy. So as Valentina mentioned, I do think it's important before I sort of talk about the meat of my presentation to kind of raise awareness about Denison's efforts to bring solar energy to our campus. This is our existing array. If you've taken a walk in the bioreserve, you might have seen it. It is a tracking array. I am going to close this now. The panels track the sun and rotate to follow the sun, and it produces about 2.3 megawatts of power. The new array is more than twice the size. So here is campus, there's the stadium down there, this is the high school here, and this is where the existing array is here and here. And the new array is going to be sort of off up here behind the homestead, and it's going to take up that footprint. So it's going to be about twice the size of the existing array. It's a little over 5 megawatts of power. And I think as Valentina mentioned, it's going to meet about 50% of our electricity needs through, well, not it, but in total now we will be able to meet about 50% of our electricity needs through solar, which is really, really awesome. I will just say personally, I'm super excited about this new thing. It should be starting next month. It should be operational in about a year. We've made a lot of progress, and I would say, especially students, keep pushing. There's more work to be done. There are more opportunities. I think there was a proposal to shift our heating to geothermal, and I would strongly encourage students, faculty, administrators to keep pursuing that option. So this is a really great progress, but there is more work to be done. So I'm going to kind of switch gears and talk a little bit more with a global focus towards our energy systems and kind of how we think about energy and what needs to happen. And I'm going to sort of frame this in 4 parts, think a little bit about kind of where things are today, maybe where we're headed, my case for why we should be using solar energy, and then some other really essential parts that we need to manage as we move forward to make this all work. Okay? So first of all, it's really, really important to understand how central energy is to pretty much every goal that you might want for human progress. So things that you know, clearly we need energy for jobs and for commerce and things like that, but we also need energy for education, for healthcare, to bring up infant mortality rates, all kinds of really crucial aspects that without energy, we cannot purify water, we cannot cook our food, we cannot empower women to, you know, have other opportunities besides fetching fuel for cooking, which many women in the world spend most of their days simply collecting wood to be able to cook. Okay? So when we talk about energy on this scale, what we're looking at is understanding how energy can really promote this human development. So there's this plot here showing this Human Development Index, which is sort of this combination of life expectancy, education level, and per capita income. And what you can see is there's a pretty clear trend across the world where having access to not very much energy creates a huge rise in this Human Development Index. It doesn't take much. So having no energy versus having a little more energy, in other words, moving slightly to the right on this graph, causes a huge growth in this Human Development Index, and that is incredibly important. And what you can see, though, is that it then tends to plateau. And I don't know what they're doing out there in Iceland, but it's cold out there, I'll give them that. So I think a lot of that is coming from their heating. Luckily, they use a lot of renewable energy in Iceland. But the point is, it would also be nice if we could move that way. In other words, if we can maximize our Human Development Index and still keep our energy consumption reasonable, that's really ideal. So with that in mind, it is important to sort of understand the scale of energy in the world today. And so there are many units of energy, and they are very confusing. And so I've tried to mostly convert my units of energy to something called a terawatt. But to understand what a terawatt is, you have to understand what a watt is. So a watt is a unit of power, and basically the thing in your pocket right now, your phones, consumes something like a watt of power. Okay, it's not very much. If you combine 1,000 phones, you would get a kilowatt, and that's about what a microwave consumes. If you have 1,000 microwaves, that gives you a megawatt, and that's about what a small jet engine would produce. 1,000 of those would be about the scale of a nuclear power plant. That would be a gigawatt. And the scale of all the electricity, not all the energy, but all the electricity on Earth is on the order of about a terawatt. So about 1,000 nuclear power plants, okay? So we're gonna talk a lot about terawatts. It's a huge amount of power. When we look at where we get our energy from today, what you will notice is that it is largely fossil fuels, whether that be oil or petroleum, coal, natural gas. Those are the biggest players. This is actually, I take that back, this is in 2016. And if you compare it to, I think what I have is 2022, what you'll notice, I'll transition in a second, what you'll notice is the change is subtle. So what you'll notice is mostly it changed right there. Not that much change here. What happened was the renewables grew in. And that's great news. What's happening here is the world continues to grow. We continue to expand our energy needs, and that new need is largely being met by renewables. What is not happening, however, is we are not reducing our fossil fuel use. In fact, it is also increasing. Okay, so we have not weaned ourselves off of fossil fuels. If you look at this trend over, a few sort of 5-year windows, what you'll notice is the total percentage of fossil fuels has slightly shifted, but mostly the biggest changes have been here in these renewables. We've gone from basically no renewables to a fairly substantial but still small minority of power. But our energy consumption in total has continued to grow over this period. If you look at where that growth is happening, we can look at this trend in different regions of the world. And what you'll notice is the United States is here at the bottom, is very thick, but also not dramatically increasing. Okay, it's relatively stable. Other parts of the world, though, are rising rapidly. And those other parts of the world are primarily these 3. You can see that right here. So if we look at this trend, a lot of this really large growth over the last, say, 20 years is happening in particular in China. So if you compare China in 1980 to China today, it went from being about 6% of the world's energy to more than a quarter of the world's energy. Huge, huge growth. And that is because they're doing their best to bring their people out of poverty, and that takes tremendous amounts of energy. And the other aspect is there are a lot of people that live in China. But other areas which are growing rapidly are also Africa. Okay, and the rest of Asia is also growing. Other parts of the world have shifted, but not nearly as dramatically. And we can see this when we look at our carbon emissions, again, coming from different parts of the world. You can see here, this line is China, and they have simply, since about the year 2000, ramped up their emissions dramatically in that time period. And so now they are by far the largest emitter of carbon dioxide in the world as a nation. 2 things that are worthwhile keeping in mind. We have been emitting at a steady pace for many, many years. And so historically, cumulative emissions, we still lead the way by a long shot in total cumulative emissions. And it's also important to keep in mind the relative populations of China and the United States. So the United States is about 5% of the world's population, I think something like 4% actually, and we consume about 15% of the world's energy. So on average, we consume about 3 times more energy than your average global citizen. Okay? If you look at carbon emissions per capita, even though China is by far the bigger emitter as a nation, the average American produces about 2.5 times as much carbon as your average Chinese citizen. Okay? Again, I don't know what they're doing up there in Qatar, but they are producing a lot of CO2 there. On the other hand, you can also see places like Haiti and Somalia producing next to nothing. So, you might wonder, why do we continue to use fossil fuels? And the fact of the matter is, fossil fuels are truly amazing. There is a reason we use them, there is a reason we continue to use them, and there is a reason they are so hard to give up. They provide us massive amounts of energy. They are extremely abundant. You poke a hole in Saudi Arabia and oil comes up. There are mountains full of coal in the United States. There's just massive amounts of this stuff. It has huge energy density. It doesn't take much, and it provides me a lot of energy. 1 tank of gas is the same as 80,000 iPhone batteries. Tank of gas that you put in your car in 3 minutes, which, by the way, allows you to drive 500 miles. In 2 minutes, you fill up your car and you can drive 500 miles. That is incredible. Stuff is stable. It's been around for 1 million years, right? It's not going anywhere. And because it's a liquid, we can transport it easily by pipeline. There is something like 100,000 miles of pipeline in the United States. Pretty impressive, okay? So it's no wonder that we use so much of this stuff. When we think about, why we might want to transition, many people say, oh, we have reached, we are going to reach peak oil. And there's concerns that we're going to run out of fossil fuels. And frankly, this is nonsense. We are not anywhere close to running out of fossil fuels. They may begin to get more expensive as they become more difficult to extract, but there are still many, many years of fossil fuels available. So here's our usage. This is 2016. It doesn't really matter. I had to multiply this box by 10 so that you could even see it vertically. Otherwise, it just looks like a line. And this is the amount of coal that is available out there in the world to us. Okay, so one way to think about this is, the fossil fuel age is not going to end because we ran out of fossil fuels. We can keep burning fossil fuels for literally millennia. In the same way, the Stone Age didn't end because we ran out of rocks. Okay, and there are other sort of additional occurrences of these fossil fuels, which now I had to multiply this by 100 to be able to see it. If you look sort of in slightly less economically accessible places, there is just massive, massive amounts of energy available to us. The other thing which is important to keep in mind is the cost of solar and wind has really, really plummeted in the last 10 to 20 years. It has gone down dramatically such that now renewables are in fact the cheapest option in many circumstances. In many places in the world, building new power installations, the cheapest option is in fact solar. So here's coal, relatively expensive. Natural gas is now very, very cheap, but even still, wind and solar are beating it. And yet, they still only contribute something less than 10% of our total energy production in the world. Why is that? And there are a few reasons for that. Okay? First and foremost, many, many things that we do in the world today rely on fuels and not electricity. So most of us, when we drive using gasoline and not electricity. Some of us might have EVs now, but mostly long-distance trucking, shipping, airplanes, that's all based on fuel. Most of us, when we cook, we're using fuel. A lot of heavy industry is based on burning stuff, and that stuff is largely fossil fuels. In fact, only about 20% of the world's energy comes from electricity, but these renewables primarily only generate electricity. Okay, and so that's not the most useful form of energy. In other words, the world really runs on fuel and not electricity. Okay, and that's very important to keep in mind. And yet these renewables only make electricity. So there's more to the story though, because even if you look at the way we produce electricity, what you'll notice is that it's still fossil fuel. So this is 2009, and at that time, things like wind and solar were prohibitively expensive. It just was not cost competitive, and so almost all of our electricity came from either fossil fuels or nuclear, and there's some hydro here, but other renewables, wind and solar, is just a tiny slice. What you'll see is that when I switch to 2022, the ratio has shifted. And now you can see that green slice of the pie has increased dramatically, but it's still a small minority. The other thing that changed dramatically is the amount of natural gas grew quite a bit, and the amount of coal has gone down a lot. Okay? So there are many reasons why we do not have a completely renewable grid. Some of that does have to do with gridlocked politics, short-sighted policies, entrenched interests, which are not, interested in making more money off of the fossil fuels that they sell and would like to keep their interests in place, as well as infrastructural inertia. If you want to replace every single gas station in the world, that doesn't happen overnight. There's a lot of buildings, a lot of tanks, a lot of refineries that have all been built around this system. And even if we said, okay, we're done with gasoline, it would simply take time to stop using those things. And if you just built this thing and spent a lot of money to build it, you don't want to just give that up. Okay? So the question I want to think about is, aside from those aspects, is there a technological issue that we also still need to overcome? Is the science ready for this transition? And I would argue yes and no. Okay, so one of the aspects that we need to deal with is the fact that on the energy grid, supply must constantly meet demand. In other words, to sort of take the analogy a little too far, if I turn on the lights or turn on my air conditioner, the folks at the power company need to shovel a little more coal onto the fire to make a little more electricity to balance that out. Okay? At every moment in the day, supply needs to meet demand. And what can happen with something like renewables, where we don't get to control whether a cloud goes across the sky or the wind is blowing or not blowing. And so sometimes renewables might not meet demand, and sometimes they might exceed demand. And if we have other sources of energy on the grid, when it doesn't meet demand, we can burn some natural gas and compensate for that. But it causes real problems for us when, in fact, it's making more electricity than we have the capacity to put out there on the grid. Okay? And so what happens is something called curtailment. Okay? So it's these peaks here that cause this issue. And what happens is something called curtailment. So here's a simulation of a given day in California, and this is a summer day, and you'll notice we're using a lot of power, and as the day goes on, power rises, and this is sort of more and more solar power, and here, because we need a lot of energy, solar power is great. It's offsetting this very large need for energy, and it's all good. In fact, it's doing something called smoothing to the demand curve, where it makes it easier for grid operators to meet the quickly rising demand. The problem is, if instead you had a nice, pleasant spring day in California where energy consumption is much lower because not everybody's cranking their AC, demand is moderate, and yet it's still a nice sunny day. And now what happens is we have more solar than we know what to do with. And so what they do when that happens is they simply shut off the solar panels or turn off the wind turbines. And that's fine technologically, but if you spend a lot of money to build those and install those solar panels or those wind turbines, your investment is not paying off now. So as an investor, as somebody who may want to build this, that financial commitment isn't very attractive if you're like, well, they're only going to be using my power 75% of the time because they're going to curtail it when they don't really need it. Why, I'm going to make less money, so I'm not going to invest. It would be nice if we could do something with that excess electricity rather than just simply waste it. The other aspect of this is, while it's often sunny in California, you may have noticed the weather outside is not so sunny. And in February in Ohio, it's not very sunny. So seasonally, there are also pretty big changes. These are my solar panels. This is data from my house over the last, 7 or so years. And what you can see is the amount of power that my solar panels produce in January and December is literally 4 or 5 times less than what I get out of my solar panels in the summertime. And that's a combination of two things. The weather is more gray in January and February around here, and also days are much, much longer. So even in California, where it's sunny most of the year, days are still shorter in the wintertime, and so you get a lot less sunlight. Okay? The problem is, that's what my solar panels are producing, but what I am using is fairly constant. Now you can see there's some variations. In the summertime, sometimes it gets hot, we turn on our AC, and that causes a big spike in our usage. Here's when we started plugging in our EV into our house and started using a lot more electricity. But for the most part, across the year, our usage is fairly constant. And what that means is, because I have a grid-tied system, in the wintertime, I'm largely relying on the grid. So here is sort of my net consumption across a year. And what you can see is about half the time, I'm pulling energy off of the grid, and half the time I'm making more energy than I need. And for me, that works great. Absolutely no problem, because I have a grid-connected system, okay? So literally in the summertime, my electricity from my solar panels goes to my neighbors, and the power company pays me for that. And that's great, works perfectly, no problem. And in the winter, I'm connected to the grid, so I just get my energy off the grid, works great, no problem. I get a little bit of payback, a little bit of sunlight, and it works fine. But if the whole world was trying to operate off of something like this, either we would have to build way more solar panels than we needed to get enough power in the winter, And then we would have way too much in the summertime, or we need some way to store that energy. And we're talking about massive amounts of energy. You can see that sometimes I'm producing about a month's worth of excess energy in the summertime, and I have no way to store that much energy. So I might be able to store it from hour to hour, day to day, but not over months like this. So my conclusions for this part are that fossil fuels are incredible. There's this reason that we use them. We are rapidly shifting to renewables. I would argue not nearly fast enough. We'll talk about that in a moment. And there's no fundamental reason why we cannot rapidly continue to expand solar. At the point we're at, we still use very little. And so this problem with needing to balance storage is fine. We could reach much, much higher levels of solar and it won't be a problem. But eventually, if we wanted to run our entire energy system off of renewables, we will have to deal with this storage question. But right now, we're walking this path. We are not implementing renewables as quickly as we need to. And so I just maybe provide some scary slides about where we're at and where we're headed. So first of all, I don't think I need to convince anybody in this room of those three things, but I do think it's important to see exactly where things are at. It's easy to tune out these things. This is some quotes from this IPCC report. I'm not going to read these, but it is unequivocal what is happening here. And I will sort of point your attention to this comment here, which I think is really important. Vulnerable communities who have historically contributed the least to climate change are disproportionately affected. In other words, the folks who have done the least to cause the problem are being affected by it the most. And that seems very problematic to me. If you look at trends in global temperatures over time, you know that they are rising. It's a little bit hard, I think, to kind of understand what these plots show. So I have a couple of different videos to kind of help see these trends that I think maybe illustrate it a little bit better. So this is going to show temperatures. It started in 1880. It'll play again. We'll see it again in a second. Over time, so this is 1 year, and that is showing basically that same plot. So you can see here the temperatures at the beginning of the 20th century, and there's some variation. And as we approach later and later, and that's 2024 up there at the top. There's a stable pattern, and recently it has just started going through the roof. That's one way to visualize it. Records are being broken every single month for about the last 2 years. Here's another version. So this is exactly the same sort of data set. Starts in 1880, and it shows global temperatures across the world. And you can see, again, at the beginning of the 20th century, there's some blue areas, some red areas, cold and hot. And as we start getting into the later part of the 20th century, things start looking radically different. Radically different. That was 2023. Here's 2024. Red is hot. Things are changing, and it's really fascinating. You sort of listen to the climate science, and there's a lot of things we do understand, and there's a lot of things we don't understand. But almost always, things have gone worse than what we expected them to do. There's a tight correlation between CO2 and temperature, this sort of hockey stick plot showing both CO2 levels and temperature rising. Again, I think it's useful to put this in perspective. So here are global temperatures over the last 800,000 years, about 1 million years worth of data here coming from ice cores, showing the tight correlation between CO2 in purple and global temperature in yellow. And you can see that they are tightly correlated. Now, there is a difference between correlation and causation, but they are tightly correlated. That much is clear. And that is the last, as I said, about 1 million years. Today, we are up here somewhere. We would have to rescale it, so let's do that. Last million years today, 425 parts per million CO2 in our atmosphere. If we continue on the path that we are currently on, even continuing to rapidly expand renewables in the way that we are, but we just keep doing what we're doing, which we're making lots of progress, right? Again, would be off scale. We would be somewhere around something like 750 parts per million. Estimates vary. Obviously, we don't know what's going to happen in the next 75 years. Might be as high as 1,000. Maybe if we stopped burning everything literally tomorrow, we could hit 550. So here's the last approximately 1 million years down here. By the way, ice ages have come and gone during that period. That's where we're headed in the next 75 years if we keep it up. The other aspect is this stuff does not go away. Once it's in the atmosphere, it stays in the atmosphere for centuries or millennia. So about 3/4 of it goes away in the first 100 or 200 years, but it takes literally thousands of years for the remaining 25% to go away. Effectively gets absorbed by oceans and rocks. Okay. So as we stand here, in the immortal words of Clint Eastwood and Dirty Harry, you've got to ask yourself if we feel lucky. Right? We don't know what's going to happen. And the problem is that climate modeling is not good enough to tell us exactly what's going to happen. And by the time that the climate models do tell us exactly what's going to happen, it will have already been too late. Okay? So we need to decide what to do. In fact, inaction is a kind of action. Not doing something about it now is a choice. And the only way to know for sure what's going to happen is to do it. But we only get to try that experiment once. Once it's happened, there's no going back. So if we want to do something about this, we need to find some way to make energy. We need energy. Humans need energy. I hope I've made that clear. And to make a dent in this problem, we need to generate something like 20 terawatts of energy carbon-free. So that's essentially as much energy as the world produces today in every form, 80-odd% of that coming now from fossil fuels, but now entirely carbon-free. And there's a number of ways that we can do that. And I want to make perfectly clear, we should be doing all of these, okay? I really want that to be clear. I am not saying only do solar, but I am going to make the case that solar must be central to our efforts. And the reason for that is really very, very simple. If you look at the amount of energy that humans use on Earth, so all of the energy that we use, say, in a year, and you compare that to the amount of energy that is available from the sun, the area of that circle would be how much energy we use. The area for how much energy is available from the sun wouldn't fit really in this room, okay? It is colossal. If there's one sentence that you remember from this talk, remember this one. As much energy from the sun strikes the Earth in 1 hour as the world uses in a year. The potential for solar energy is colossal, okay? And it is far, far larger than any other source of renewable energy. And in fact, every single source of energy, aside from nuclear, is actually recycled sunlight. Fossil fuels are recycled sunlight. Wind is driven by the sun. Waves are driven by wind, which is driven by the sun. Biomass is driven by the sun. It all is, in fact, different forms of sunlight, okay? So if we put this to scale so that we can see the whole circle, now the amount of energy that humans use on Earth is much, much smaller. And if you compare that to other renewables, what you'll see is that, yes, the amount of energy that wind can produce is about the amount that we need. But it is still a tiny fraction of what sunlight can provide. And if you're trying to meet all of human needs with something which, when we get every square inch of the Earth covered in windmills, we can barely meet our need, that's not a good combination, okay? We need something like 20 terawatts, and in principle, we have accessible to us on the order of 600 terawatts, okay? When we think about how we use solar energy, there are a number of different ways you can do it. You can use basically the thing that maybe you did when you were like in elementary school. You can take a magnifying glass and heat something up really, really hot by simply focusing the light on a point. You can do nature's way, which is to produce plants through photosynthesis. Essentially what you do is you take carbon dioxide and water and make CO2. Take carbon dioxide and water and make sugars, which is of course what the plants are made out of. Most solar panels that you see today are so-called photovoltaic devices, and they take sunlight and a semiconductor junction and produce electricity, and they only produce electricity. The type of research I do is focused on this middle area, which is called a semiconductor liquid junction. And what's interesting about these is while plants can only produce fuels, right? Wood, plant matter, photovoltaics can only produce electricity. A photoelectric chemical cell, or a semiconductor liquid junction, can produce both or either. I'm interested in using this device to make hydrogen and oxygen from liquid water. Okay, so let me tell you a little bit more about how these work. So solar thermal, literally you take a parabolic mirror and you focus it onto a pipe, and that pipe is a fluid. This stuff gets so hot that they use a molten salt. And once you have this very hot thing, you can basically use that to boil water. Boiling water makes steam, spins a turbine. That's how we make electricity today. It's great if you live in a desert. You cannot focus light which is diffuse. You need direct sunlight. So if it's cloudy, you can't focus light anymore, right? If you try to use a magnifying glass on a cloudy day, it doesn't work. In a place like Ohio, this would be terrible. But if you live in Arizona, it's great. Problem is that most people don't live in Arizona. They live on the East Coast, in other places. And so there's a mismatch of where folks live and where there's all that sunlight. Photovoltaics is, of course, sort of the most common. This is what Denison has just built and we continue to build. And these can be quite efficient. Their costs have come down, but they only produce electricity and there's no possibility of storing that electricity through these modules. As I said, what I study are photoelectric chemical cells, and these are largely still in the research phase. These are not, for the most part, sort of commercially available options. And the reason for that is they've had relatively low efficiencies so far to date. And so that's why there's a lot of research interest. But they're relatively simple to make. You literally take a semiconductor, dip it into a solution, and shine light on it. But the problem is the cost to amount of fuel that you make is not attractive yet. So that's why I'm interested in moving that forward. So as we think about how we might solve the energy crisis, avoid climate change, we really have to make sure that solar is part of our energy mix. It's really the only thing which has the capability of meeting our needs now and forever. But certainly we should be taking an all of the above, and I mean all of the above in terms of renewables and carbon-free options. That would include wind, geothermal, ocean, you name it. But all of these things are not ready to meet the demand that we have today. We are a long ways off from being able to implement these, and they are all going to have trade-offs, right? If we want to build massive solar arrays, we might have to cut down some forests. We might have to build them in a desert where there are native plants that maybe will not benefit from having solar panels built all around them. There are going to be trade-offs. I want to make sure that to emphasize that even if we had free, infinite solar panels tomorrow, there are still issues to work out. And part of it is we emit a lot of CO2 from other things. Agricultural emits a lot of CO2. Concrete and steel production emit a lot of CO2, things like deforestation. And while we're moving towards electrification, in other words, moving away from using fuels, right? Lots of EVs on the road today, moving away from heating our houses with fuels and using things like heat pump or geothermal. It's still relatively limited in scope and not nearly enough. pretty much all long-distance transportation will remain driven by fuels for a long time to come. And if we rely on these things, we may require lots of new infrastructure to move electricity around the country. If we have windmills, say in North Dakota, again, not a lot of people in North Dakota, lots of wind, but we got to move that energy from one end of the country to the other. And electricity is devilishly hard to store. So these last two are sort of what I want to focus on for the last part of my talk. When you think about moving electricity around the nation, you might look at our grid and say, hey, we've got this grid. There are wires everywhere. It's all interconnected. And it looks that way, but it's not. In fact, the grid looks something more like this. There are these different regions, and they largely don't talk to each other. Texas has its own thing. Texas just does their own electrical grid. That was part of why, I don't know if you followed this in the news, but I don't know, maybe it was 10 years ago now, there was like a major energy crisis in Texas. Their whole grid shut down. Part of it was because they were independent. But the issue is if power is being generated on the West Coast, it has no way of getting to the East Coast. Those are not connected. And if we want to bring power from one side of the country to the other, there simply isn't the capacity. So we need to build lots and lots of new power lines. And you might imagine if somebody said, hey, I'd like to build a massive power line through your backyard, how do you feel about that? You might not be too excited for them to build that, despite your understanding that it's an essential need. Or if they said, hey, we need to build a massive power line through Yosemite National Park, how do you feel about that? You might also not like that so much. So these kinds of issues are very real, and it takes a lot of time to build that kind of massive infrastructure. And right now in this country, that seems to be very, very difficult. The other aspect, which is more technological, is how do we store energy? So another way of dealing with this problem would be to store the energy, right? If we could store it, say, during the day and use it at night, store it over the summer and use it in the winter, but we really don't have technology to do that. And when I said, are there technological limitations to implementing solar, what I was talking about is this. So solar, ready to go. No problems there. It is ridiculously cheap. We are mass producing it. Cells are getting more and more efficient and cheaper every day. What we have not yet solved is the storage problem. So when we look at what's available for storage, there are a number of different technologies, and it turns out that the best way to store electricity in massive amounts for long periods of time is the least fancy way you could possibly imagine to ever do this. It is something called pumped hydro. Pump water uphill when you have energy, let it flow downhill when you need energy. It's not fancy lithium-ion batteries or other cool technology. It's pumped hydro. And in fact, 90-odd% of global electricity storage today is in the form of pumped hydro. But if we want to massively expand this, what you need is a high reservoir and a low reservoir. And if you live in a relatively flat place like Ohio, you might not have two reservoirs that are hundreds of feet different in elevation that are close to each other. And so it's hard to build these things in many parts of the world. But it works very well, and these things are huge. So here's a picture of the turbines, and I'll zoom in so you can see more clearly. These are people here. And so these are the various turbines. These are massive, massive structures. Part of the reason why we build things like this is to do something called load shifting and load leveling. So typically during the nighttime, humans don't use a lot of energy because we're sleeping. And then when we wake up, we suddenly start using a lot of energy. And during the day, we use a lot of energy. And then we all come home and cook our dinners, another little peak. And then we start going to sleep and it falls off again. Okay? And power companies spend a lot of time predicting these curves. And so they know what's coming. And they work very hard to meet this rapidly rising demand, because as I said, supply needs to meet demand on the millisecond level. You can use short-term storage where when you're not needing much power, but you can still generate it, you could make more power than you need and store it, and then take that stored energy, and release it when you have a lot of demand. And so rather than trying to meet this very steep rise and fall off every day, you would have a more level load. That's currently mostly why power companies are interested in storing electricity, is to manage this load leveling, and it makes it easier for them. If we want to implement solar on a massive scale, we would need a different level of storage. And when we think about the way we store energy, one of the issues is that energy density in a battery is extremely low. So there's a reason, for instance, our bodies use chemical fuel, right? Sugar, fat, very high energy density. Here's natural gas, hydrogen, and even the world's best batteries are still very, very low energy density. Now, if you have a massive installation and you're just using it for, a stationary source of energy, who cares how much the thing weighs or how much space it takes up? That's fine, we have plenty of space. If it's just sitting somewhere, it doesn't matter if it's heavy. But if you want to use this for a car or a truck or a ship or an airplane, you care very much about how big it is and how much it weighs. And that is the problem with something like an electric vehicle, is if I burn gasoline, say, what I carry around in my car is gasoline. I don't need to carry around the oxygen because there's oxygen all around me, and my car sucks in oxygen from the air. And guess what happens when I make the water and the CO2 that is produced? I dump it out the back, and I don't have to carry that around either. The difference in a battery is, by definition, what makes a battery is it is self-contained. I have to carry around everything, right? An AA battery, it's all in there, the reactants and the products. So instead of carrying around 230 grams, I have to carry around a kilogram, basically 5 times as much, just based on the chemistry alone. It doesn't matter what technology I'm using. Necessarily, I'm carrying around much more stuff when I have a battery, okay? So no matter what, if we're thinking about storing energy, we want to be doing that in the form of chemical fuels, not in terms of batteries. Batteries are great, but for the scale that we're talking about, it's really always going to be better to do this in the form of fuels. So when we think about taking this renewable electricity and using it in various forms, distributing it, getting it to the places that we need it, there are lots of conversions we can do. And I'm not going to go through all the details of this slide, but you can think about, right, heating buildings with a heat pump, electric vehicles. You could think about doing things like converting your renewable electricity to a fuel and then using something like a fuel cell, making chemicals, all kinds of ways that are very important to do these energy transformations. So this idea is called power to X. In other words, take your electrical power and convert it to any form you need. Things like, rather than using AC during the day, what if when you had excess energy, you just made a bunch of ice? And then when you need your AC, you run your building's air over ice, and that cools it down. And now you have, instead of relying on sort of peak energy, you can cool your building down with the ice that you built when you had lots of energy available, as opposed to when it was in high demand. Another way to do this is to directly take sunlight and turn it into a fuel. And that's what my research is focused on. So sort of the holy grail of solar energy, at least from my point of view, is to take water and sunlight and turn it into hydrogen and oxygen gas. We don't need the oxygen gas that's in the air around us. We would just dump that, but we would collect this hydrogen gas. And hydrogen gas would be an ideal basis for a carbon-free, completely sustainable and renewable energy system, okay? The reason for that is I can make hydrogen gas from water, and when I burn hydrogen gas, or if I use it in an electrochemical fuel cell, what I make again is water. So it's just a perfectly recyclable system. I take sunlight and water and I make hydrogen and oxygen, and then I take that hydrogen and I recombine it with the oxygen to make water again, and so on and so forth. I will point out, by the way, that the way we use fossil fuels is really the same thing, right? Where did the CO2 come from? It came from plants growing. They sucked CO2 out of the air. went into the fossil fuels, that's just CO2 from millions of years ago. The problem is that's out of balance, right? We're not making fossil fuels nearly as quickly as we are burning them. And so the cycle is out of balance. If we were growing plants, burning them as quickly as we were growing them, that would be fine. We would be emitting CO2, the plants would grow, they would suck that CO2 back up, emit it, plants would grow, suck it back up, and that would be a cycle also. But the problem is that system is out of balance, and so on net, we are causing deforestation, and we're burning many more fossil fuels than are being formed in the world today. So what I'm interested in is taking semiconductors to be able to drive this reaction. So a semiconductor can absorb sunlight and then drive this reaction. So I'm not going to go too much into the details of the chemistry of that here, but I'm interested in using a low-cost material. One of the primary constraints to all of this is that we must do this at low cost. And so I use iron oxide, aka rust. Doesn't get much cheaper than that. The problem is that rust is, as you might imagine, kind of a terrible material. It's not very high quality. And so what we're trying to do is get a cheap material to behave like an expensive one. The way we do that is by nanostructuring it. So here is sort of the system where iron oxide absorbs the sunlight, and that can produce oxygen from water. In an electrochemical cell, you always need two electrodes, so that would be linked to another electrode, which I haven't specified that material, but that would be called a cathode. And there, the water would produce hydrogen. I would collect that hydrogen and then be able to use it either in a fuel cell, which can then go on to produce electricity, or burn it to make heat, or any number of other possible transformations. The idea is to, again, make my iron oxide with nanostructures to sort of overcome its normal, rather poor properties. So here's a illustration of some work we did showing so-called cauliflower type iron oxide nanostructures, because the pieces really do look kind of like cauliflower. And what we did was couple that with some oxygen evolution catalysts made out of earth-abundant, non-toxic elements, cobalt and iron, one which produces hydrogen. So this is a hydrogen evolution catalyst from nickel and molybdenum. An oxygen evolution catalyst here, combined with sort of one of the cutting-edge technologies of new photovoltaics, a perovskite-based solar cell. And altogether, this allowed us to rather efficiently produce hydrogen gas from sunlight using low-cost, non-toxic, abundant materials. And so we're interested in pushing this further, and by thinking about these sort of novel architectures, nanostructuring, and incorporating catalysts, we can make this process far more efficient without increasing the cost. So let me just conclude here. I hope I've convinced you that energy is absolutely essential to human progress, and I think most of the goals that you all, I think, share with me in terms of what we would like to see happen for civilization. Climate change is real. It's scary. It's one of those things, honestly, where the more I learn about it, the more scared I get about what the future will bring. But I think there are many, many opportunities to do something about that. I wish there was leadership helping us along that path. But if we don't do anything, where we're headed is pretty clear. And we really need a transition to a carbon-free energy system as quickly as possible. And the clock is ticking. If we're going to do that, we must rely on sunlight. And the simple answer is because that's where the energy is. There's a silly joke. Somebody asked famous bank robber Willie Sutton, "Why do you rob banks?" And he said, "Because that's where the money is." Why should we use solar? Because that's where the energy is. But there's more to it than that, and thinking about what we do with that energy is equally important. How do we distribute it? How do we store it? How do we transform it into other useful forms? Those are all incredibly important parts of the puzzle that we have not yet completely solved. So with that, thank you very much for your attention, and I'd be happy to take any questions.